welcome back. Today we're going to have a look at, or an update with the Math64 library and a few things about revision, the demo party 2021. First, let's get stuck into the Math64 stuff. Down here to showcase. It's the development thread on the forum. If you're not sure, made a little logo for it, as you do. You might have read most of the stuff in here. A few updates in the past. What I've done the last session or so actually is I've made improvements to the lexing and improvements to the compilation. Just see if there's an example up here that shows a picture of what I'm talking about. Here, actually, yeah. Oh, no, it doesn't actually, sorry. In the previous versions, you would get lots of temporary copies between, where if you do like an addition between vectors, this creates a temp vector and then the result is copied out into the actual target. Move, copy. Oh, there's an example there. I've looked at the line here. We've got a vector addition between the vector at stack offset 5 and the vector at stack offset 7, and the result's been stored at offset 9. Then on the next line, we're copying 9 into vector 5. So if you look up here in the code, what we'll see is where this addition is. I'm assuming it's this line here actually. We've got position plus position, position equals position plus speed. So this is being broken down and becoming two separate operations, or it could just be one. So in these older versions of Math64, we get an extra instruction being produced. Now at the moment I'm doing about 50 things on the computer, so I can't really do any accurate timing, but we'll fire up PlayBASIC. The actual framework hasn't changed at all. I've been changing the back end of the library as it stands. Our particle processing routines are about the same. That's the internal processing routine, and that's the script version. If we look at the script code down here, on the test, we've got some declarations of a 164-bit float, 2 vectors. We're doing an addition of a vector. So this would generate a temp before. Now it no longer does. And the speed y doesn't produce any temps as well. We do get some ugly code produced for this section here. So if we run this now, we're going to run. We've compiled it. We've got our variable list over here. We should have our code list over here. Now you'll notice we've got our add vector as a straight throughput, our add variables a straight throughput, our call function to do the range. So we're looking at this code here, if range, blah, blah, blah. Go back to here, call function, then a branch on the status of that previous call, which is what the if statements boil down to being actually. I think what we could do here is we have range and if be probably a separate function. If it sees that you are passing it a literal sense here, so we're comparing the position vector here. We're comparing the x-axis to this bounds of the screen coordinates, which are both literals. Now clearly, if we have a version of that range function that can do that inside, compare the x to a pair of literals, we don't have to have temporary variables and this kind of stuff impeding our variable tables. We need to have an exit function in here. We haven't got one, but we need to have that in there somewhere. Go back to view. But our particle processing code is down to here. Now we can get this down lower. As I was just saying, if we bundle up some of these a range comparison with the branch comparison as well. It could detect if the two things are following each other quite easily actually, and then do what it needs to do. Look back at the code here again. So when the particle is being processed, we're adding its speed to the particle's current position. We're altering the y of the speed to give the illusion of gravity on the particle over time. We're doing a range check to check if the x is inside the bounds of the screen. So this determines whether we draw the particle or not. And then on the y-axis, because it can be outside the y-axis but still be okay to actually do something with. I think here if it's inside the screen bounds, it falls through to compare on the y-axis. We're doing a Boolean expression here, comparing the y component to the bottom of the screen and then the top of the screen selectively. So if it is above the top of the screen, we don't delete it. We keep it processing it until it actually comes back into view. A lot of those particles will leave the top of the frame and move outside the screen bounds on the x-axis eventually. But some will return. Let's go back to here. Familiarise yourself with the particle limit. This is just PB processing as normal. I'm downloading a bunch of crap in the background, doing all kinds of stuff. So we're not going to get much of a benchmark out of this, but we get the same result. That's the key point. We're getting the same result whether we use internal processing or whether we use the Math64 library, which is good. Now, one of the points I wanted to get to is I mentioned this a while ago about lexing. So the lexer is this bit of code that's doing the classification of what the text is. So it's a very simple loop. It just runs through the string, character by character. It makes an assertion about what each character is. If it's numeric, it goes, okay, this is probably a number. We look at the numbers, etc. So I've added a few extra things to this version. It can support the hex and octal with PB supports. We can support a string there as well, which is kind of useful. We've got a hex literal. What else we got? We've got like a single line remark, which can be trapped inside it, and output as a normal remark. And the reason I added those things is not really because I wanted to update the script to do this stuff. Is the conversation I was talking about a little while ago about, I'll just change the example program here. This is an example source that has a bunch of these tests in it. So I've got a hex literal at the top there. This is just padding to make sure that the phraser is picking up the token correctly. This is an octal value, an empty rem statement, a single line remark, a semicolon for a rem statement, etc. Double lines. It does handle strings as well, as you can see down the bottom here. We've got string literals being supported, hexadecimal values, etc., and binary values as well. The reason I've added or updated the phraser to support those things is from this conversation I was having with you earlier, I should say, months ago now probably, is that we need like a secondary tool that can do lexing of PlayBASIC code. And I don't mind if it's kind of a standalone library that just does this. So for things like, for people who want to do pre-processing of their projects, you could pull a library into your code, pass it the code as a string, and it spits back this it's a structure pretty much in memory that represents the file and what classifications are. It pre-classifies what the string you pass it is made up of. So things like keywords will give you a handful of internal keywords. It doesn't know what variables are. It has no concept of that. It doesn't know what a function declaration. None of that kind of stuff. It's just breaking the text down into, this is a a word, this is a bit of white space, this is a bracket, this is, you know, a multiplication sign, this is, you know, a division, an integer, or whatever it's going to be. So your code can just pick through and look for the thing that's interested in and do a replacement perhaps, or insert something, or delete something, or modify something, and then dump the tokens back out to a string, which is what the pre-processing ideas I was talking about earlier on would need to do. But asking you to write a complete phrase off the top of your head, if you've never done it before, is a big ask. You know, I thought about doing it as just dumping out the libraries in a big chunk of a big ball of PB code, which will work, but it's a lot of code to dissect for people when you can just have the library be external. And since it's already part of Math64, we can kind of split it away and update most things that you would need. There's probably going to be some things that it won't support, like always. I mean, you won't get all of your things covered, but you'll get most of the bases covered, I would say. The current implementation here doesn't retain white space. To do this properly, you have to retain the document as it exists. So things like spaces and tabs and that kind of stuff will need to be kept, which is why that when this code here is syntax highlighted, none of the indentation is in the output, and none of the spacing between any of these things is actually accurate. It's at the end of each keyword, or the end of each token, like this word here, speed, it's seen as just a word, a bit of text that happens to be, that word might be a variable name, an array name, in this case it's a vector name. You would have to make that classification yourself. So it's not going to be a compiler, it's going to be the pre-classifying bit of code. That means you can just give it your bit of code, tell it to lex this thing out for you, use the tokens to run through and find the things you're interested in. So you're not really doing any string processing, you're just kind of going through and going, I want to find all of the words in the document that happen to be speed. Yeah, now you could use, techniques like just using in-string and replace. Yeah. But if you use in-string and replace, then you'll find every occurrence of that keyword. So if speed happens to be inside a string, you'll find speeds inside strings. And you'll also find speed as a subword of other words. So speed and speeding would be the same. So you need logic to deal with that stuff. I've used both approaches in the past. Lexing is a much easier way to go, even though it's more cumbersome initially. Right? I'll probably try and add a bit more flesh to the lexer in this, add a bit more logic to Math64. We've got some shortcutting, as I mentioned before, of these operations. So I can do, I have to find the script, won't I? Right, so we load the vector examples, go to run, and we haven't compiled it, but we've got a syntax highlighted version of it. So we've got a 2D vector stuff here, getting a normal of speed. This is something here that I want to get rid of, actually. I want to have like a vector literal that makes kind of sense in basic land. I guess you can just have vector 2 or whatever, and then have a bracket and have the two values beside it, and then substitute this into speed. If you did that, then this get normal could be pre-computed at compile time, because it knows that it's actually a constant, it's a literal. We could do something along the lines with this. Could track the status of that as it goes through, but let's hit compile. So we've built the code. Now we can view the code that we've produced. Scroll off the top there. And we shouldn't have many moves in this. We should have mostly, any copy operations in it. We should have mostly we're doing an operation and storing it in the result. So here we've got an assignment of the literal value 100 to this variable here, whatever that variable is going to be. If we look at the stack up here, we can see that stack offset 0 is the A variable. So we're moving 100 to variable A, moving 200 to variable B in this case, doing a multiplication. We're multiplying B by A and storing it in 2. So we're storing a result in C. Doing a bunch of moves there, doing a direct move of some value here. And the vector operations here, we're moving. So this is, let's view the actual code. Look at the vector operations. There we go. So we're going position equals position plus speed. Position equals position minus speed. Let's look at the code. It does that bit there, which is this section here. So now we've just got, our opcodes have come down to, we have 4 separate opcodes that do that. That's those 4 lines of code. Before that, that would have made 8 opcodes. There would be the vector addition, then there'd be a copy that copied the result out of where it was stored into this target variable. We don't need that anymore. Straight function calling stuff, we're calling cosine here, store offset 0 was variable A. That's how you read this stuff, by the way. Got some more literal stuff here. These are vector 3s this time, and those have been supported. We've got one copy operation popping up down here, so we've got a cross product 3D, and we're not catching the vector that's coming out the end of this. So it's being stored in a temp in offset 30, wherever this, there it is. There's the temp vector here at offset 30. And it's being copied across to 24. So 24 is what? It's the cross product of vector 3. That's why I wrote this little example thing, so I can actually kind of view what's going on inside the script stuff, which is really handy for understanding what's going on sometimes. Some very old bugs in PB were caused by the compiler spitting out sometimes an extra instruction where it shouldn't, that normally would mean nothing, but sometimes would break expressions. What fun, what fun. So we have 2 copies here that shouldn't be there. If we update the catching code that does the write out from the assignment side, we should be able to catch those, and they'll go away pretty much. Get normal, yeah, get normal 2D. Another thing I like about the scripting stuff that we do have is we can do wonky things with, do wonky things with our assignments. So in our scripting language, we can have a pair of variables being treated like a vector. So here we've declared speed x as a vector somewhere else in the code. We're giving it, we're setting up the x and y components here individually. As I was saying before, we probably need some other way of doing this. Maybe you could just go speed equals vector 2, and then have, brackets. Another way of doing it is just going, set speed or something like that. Like, set vector 2 or something, set vector 2, I have speed, and the parameters after here. This one here would fit into how the Fraser and Lexer works probably pretty well. This might be confusing to people, that they might think, well, is that a function call or what is it? Really, it's just, we're telling it, hey, here's a literal vector 2. We need a way of keeping the components together. So if we have vectors or matrices at some other point, we've got lots of parameters, lots of fields. You could do it use the square bracket approach there as well. I guess that would show people this is something different. It's not the same thing. Yeah, I don't know. Just spitballing. Probably getting off the beaten track there a bit. But here we can return our vector and store it in variables, and it will overwrite this variable and the next variable after it. So we have to be careful to declare these that way, but we could get normal of, could do this as well. We could go and just not use the vector at all, just use nx. And that would use, to compute the normal, it would use this pair as that vector. That's the kind of thing that I want to implement into PB. Now, yeah, that would be problematic for some people. They would make mistakes and modify their declarations at some point, and they would break code. Yeah, granted, you got me there. That would happen. But it's just easier. You know, it just turns out to be easier. You can just be a bit more liberal about this stuff. You know, if you can catch more of these circumstances where it's a bit more friendly, a bit more easy to do something, it helps people get to the end result quicker and spend less time sussing out how to do something and just doing it. All right, that's probably enough about this. We need our lexer to be able to really understand basic PB code. So we want to split the lexer apart and have a secondary library that does lexing, that you maybe have some code, some functions there to break it up into lines and manage the lines and do that kind of stuff. And then once you're finished, just reassemble it. When I did the Amos to PlayBASIC converter years ago, I don't remember how long this was now. I had no intention of making it convert the whole language. It was not the point. I just wanted to get it to a point where it understood my own programs and could do most of the annoying conversions for you. And that's where this kind of thing is really, really useful. You could make little lexers that imported not PB code but other dialects of BASIC, and converted those things up for you and made the process a bit easier for you to shift something around. Because you'll find there's heaps of code out there in other languages that if you translated it, you might find something useful for your project, and vice versa. The other thing that's been going on over this Easter long weekend, I'm a bit of a demo fan, I'm a bit of a scene fan in general, is Revision 2021. This is a demo competition. I'm not going to make you sit here and watch all these demos. Definitely, if you're struggling for motivation, if you're wondering about, hey, what's something that people are doing out there in this case, we've got some retro systems like the Amiga, of course. There's a couple here that I thought were worth having a bit of a look at. In the Amiga demo competition down here, I'll just turn the sound off. Yeah. Look, I shouldn't have to explain why this is an impressive demo. Most modern demos on the Amiga are pretty much use a frame buffer, and then everything else is just done in software. So they're less about hardware effects than what they used to be. So this demo is probably running on an 060 of some type. Who knows how much memory it has? I have no idea. I didn't check the spec. But it's very impressive. Very impressed. And we've got Melon Design, who make great demos as well. Lots of other great stuff here. If you're not into demos, you might find it hard going. This one here I found particularly amazing. Now, I'll just turn the sound off. Amigas have a mode called ham, which is hold and modified. It's a kind of a display method for drawing or displaying pictures, for video pictures pretty much. And back in my days, that's all it was ever used for. It was like you'd show up a nice rendered image in ham but you never do anything with it. So this lovely demo here has made a whole demo out of that screen mode. The reason why people didn't use it was it's kind of tricky to work with, and he's gone through and obviously come up with ways of overcoming the shortcomings. And I think this part here is just hardware sprites on top of the buffer. My favourite part of it is where he actually starts poking fun at old school demos. Well, here he goes, for example, we're seeing a scroller with a scrolling true, well, not true colour, but certainly a 12-bit ham image in the background. Pretty amazing. Easter Island. This is running on an Amiga 500, so it's OCS demo. It might be ECS, I'm not sure. I think it was OCS actually, which is the original chipset. So potentially it could run as far back on as the Amiga 1000, which is kind of staggering. If you had said to me that you could have a scrolling image in ham that didn't feather and didn't have all the artifacts in it way back then, I would have just said no, you can't. That's pretty much what most people thought. There have been other demos that have used ham as well. It's like ham vectors, which is a long time ago now. And now he starts doing classic, we'll call them, Amiga demo effects, you know. And he starts poking fun at some of the stuff. Just think of it this way, if you'd seen this, you can see a little bit of fringing around the bottom there, little bits of fringing around here. But if I'd seen this back in the day, I would have just been horrified. It would have had to have been a video animation and not an actual demo running this. It's kind of poking fun at the old days of demos. How they all had to have certain things in them. There was like a Glenn's vector time, there was this kind of an additive sort of effect, and there was these like hot chicks and sort of that were in these demos back in the day. So he's having a bit of a jab, but it's well humoured, so it's great. The effect I like the most is coming up in a second actually. I don't know how he's doing it without having the fringing effect. I have no idea. For me, it's been this one here is the one I really enjoy actually. All right, my favourite PC demo, which I haven't actually added to here yet, apparently anyway. Just jump across to YouTube. This is Arcade by Spectrals. We won't watch the whole thing. I'll just show you the section I was blown away by. In fact, the whole thing is it's well worth you watching. So I'll leave the link on the forum, etc., and go and watch it. So I'll skip through this. Most demos have a compilation aspect when they run. Go through the section where the demo is called Arcade and has a quite a what's themed on classic arcade games. This part here, so I'll skip to that. Watching this with sounds. I love this part here. It's a fantastic idea. It's implemented so well. It must have taken a lot of work to put this together. So looking back through an arcade, and it does really, for me, it catches that sense of what it was like to walk through an arcade way back in the day when I was a young kid. It's an experience that a lot of people will never actually get these days. given that gaming has gone from the arcades into the home. But it's stunning, absolutely stunning, this demo. I don't know how it did in the comp, I have no idea, but fantastic. I'll pause that there. I don't want to make you watch the whole thing. I just wanted to make you aware. Pretty cool, a lot of stuff. There's music competitions, artwork, animations. Well worth looking at for inspiration and going, hey, how can I implement those things? Can I do those things in my own programs? Who knows? Maybe you can, maybe you can't. I guarantee you that every one of these effects in these demos here took a lot of work and effort to produce. They didn't just hit compile, run it, and have it run at a decent frame rate up front. That's just not going to happen. I quite like this one actually. It's like the idea of mirroring the scene. It's quite nice. You see this in a lot of sort of abstract geometry demos on PCs in particular. It's a very compelling effect, if you ask me. Pretty cool. All right, as I said before, thanks for watching. Get yourself across onto YouTube and check out Revision 2021. Just search for it and you'll find entries, and maybe you'll find something cool. Check out the ones I've got on the forum here, of course. That's why I put them up. Get some more work on Math64 done, get that released, and we'll press ahead as normal. Hopefully, hope you had a fun Easter, hope you did something cool, and hope everything's going well for you. See you next time. Bye.